For the last decade, every major automaker has been fighting the same electric war. Range, charging infrastructure, battery chemistry. That's where the billions went. That's what dominated the headlines. And while the entire industry was staring at the same scoreboard, measuring kilowatt hours and charging speeds, Tesla quietly walked into a different room and rewrote the physics of the electric motor. Not incrementally. Not with software at the materials level. At the hardware level. At the level where, once someone moves, everyone else is suddenly years behind and doesn't even realize it yet. This isn't just a story about a faster car. It's about a fundamental shift in what an electric motor can physically do, and what it means that only one company currently knows how to build it at scale. Here's the part that should stop you cold. The motor at the center of this story. The one humiliating $1 million supercars is small enough for one person to pick up and carry across a room. One person, no crane, no forklift. And that motor just made the performance world very uncomfortable. If you think you already understand how significant that is, stay with me. To understand why the carbon-wrapped rotor matters, you first need to understand what every electric motor before it was fighting. Not competing against, fighting against. Picture the inside of a high-performance electric motor, a dense cylinder packed with copper windings and powerful magnets. Now spin that cylinder at 16 to 18,000 RPM speeds that make a dentist's drill look relaxed. At those speeds, every gram inside the rotor is trying to tear itself outward. The magnets want to fly apart. The copper wants to expand. The entire assembly is under violent, continuous stress. And here's the brutal part. The force doesn't rise linearly. Double the speed. And the destructive force quadruples. For decades, engineers solved this with a containment sleeve, usually steel. Sometimes Inconel, the semi-exotic alloy used in jet engines, strong materials, expensive materials. But they all hit the same wall. Around 16 to 18,000 RPM, the sleeve itself becomes a limiting factor. Push beyond that, and the risk of catastrophic failure becomes real. That ceiling quietly defined an entire generation of EV motors. It wasn't a design preference. It was physics, or at least what everyone believed was physics. But there was a second problem, one that rarely gets explained plainly. Steel sleeves conduct electricity. And when you spin a conductive sleeve inside a powerful rotating magnetic field, you create eddy currents, circular electrical currents that do absolutely nothing useful. They don't move the car. They don't charge the battery. They just turn into heat. Constant, unavoidable waste heat. Every second the motor runs. This forced every high-performance EV into a painful trade-off. Build for peak power and suffer heat buildup and power fade. Or build for efficiency and sacrifice the performance ceiling. Power or efficiency. Pick one. Even the best engineers in the world were optimizing inside that trap. Porsche engineered a sophisticated 2-speed gearbox. Lucid built some of the most efficient motor windings ever produced. Both are real achievements, but they're still working around the same fundamental constraint. Tesla asked a different question. What if the constraint itself disappears? The answer was carbon fiber, not cosmetic carbon, not body panel carbon, a specialized high-tension carbon wrap that didn't exist anywhere in the industrial supply chain. Tesla had to invent the process. They built a proprietary machine that winds aerospace-grade carbon fiber directly onto the rotor under enormous tension. The finished sleeve is just 0.5 millimeter, thinner than a credit card, yet it's more than 5 times stronger than the high-grade steel it replaces. But raw strength isn't the real breakthrough. Because the fiber is wound under tension, the sleeve doesn't just contain the rotor, it pre-compresses it before the motor spins once, before a single electron flows. The rotor is already being squeezed inward. It's structural defense built into the material itself. The result, the motor sails past the 20,000 RPM barrier that once looked like a law of physics. But here's where things really change. Carbon fiber doesn't conduct electricity. Replace the metal sleeve with carbon, and the eddy currents don't shrink, they vanish completely. The waste heat that used to cook the motor from the inside simply stops being generated. That triggers 3 cascading advantages. First, higher RPM capability. Second, dramatically lower heat generation. Third, a thinner sleeve, which tightens the air gap and strengthens the magnetic interaction. That means more torque, more power, from a smaller motor. And here's why. Competitors haven't simply copied it. These advantages multiply each other. Higher RPM matters more when heat is under control. Better thermal behavior matters more when power density rises. Higher power density matters more when it's sustainable. This isn't one breakthrough. It's three breakthroughs that only work if you also solve the manufacturing problem. And that's where the real moat is. The car that proved it was the Tesla Model S Plaid, a four-door family sedan. 5 adults, luggage, daily driver range, and 3 carbon-wrapped motors producing 1,020 horsepower. 0 to 60 miles per hour in under 2 seconds. Quarter mile in the low 9s. But the number that really matters isn't the first launch. It's the 10th most high-performance EVs can deliver to war. 3 hard runs before thermal protection quietly pulls power. The Plaid, under normal conditions, it just keeps going. Run after run after run. Not because of clever software, because the motor simply isn't generating the waste heat that used to force the compromise. That changes the definition of a performance EV before Plaid. A fast EV could perform once. After Plaid, it has to perform consistently. That's a different category of machine. To be fair, the competition deserves credit. Lucid has produced genuinely impressive efficiency. Porsche's taken showcases, extremely sophisticated engineering, but both still operate within the traditional RPM ceiling. Porsche's 2-speed gearbox is brilliant, but it adds mechanical complexity to work around a limitation Tesla largely removed, and in engineering, solving a hardware constraint with better physics usually wins long-term. Here's the uncomfortable part for competitors. You can't just order this rotor from a supplier. The winding machine isn't commercially available. The process knowledge isn't published. Tesla built the equipment, refined the process, and scaled it internally. Anyone trying to catch up doesn't just need to copy the motor. They need to reinvent the factory that makes the motor. That's a multi-year, multi-billion-dollar problem with no guarantee of success. For years, the EV narrative was dominated by batteries. And batteries do matter. But underneath that very loud war was a quieter bottleneck. The electric motor itself. Tesla attacked that problem at the level of materials, science, and manufacturing physics. A rotor held in permanent compression, an insulating sleeve that eliminates waste heat at the source. Power density that resets expectations for production EVs. And the wildest part, you can carry the motor across a room with one arm. The battery war was loud. The motor war was quiet. And it may have already reshaped the battlefield. The real question now isn't whether competitors eventually respond. Some will. The question is what Tesla builds next while the gap still exists. Because while others are reverse engineering the Plaid, Tesla is already working forward.